What if I told you a single metal strand, thinner than an inch, can hold hundreds of people over a cliff, and know it every single second? Every year, the world builds structures that cannot afford to fail. Cables for gondolas, chains for cranes, reactor heads holding back pressure like the lid on a volcano. But almost no one knows why these things don't snap, crack, or kill. There's no magic here, just math, control, and processes nobody talks about out loud. In this video, you'll see how metal is twisted, welded, and pressed so it lasts for decades. And if you stick around till the end, you'll learn where the weakest point actually lives in any eternal steel structure, and why almost nobody sees it. The cables for the Pisval Grande A5 gondola systems by Fatzer AG aren't simple ropes. They're multi-layer monsters with a diameter, as already mentioned, of less than an inch, made from high-strength wires with built-in fiber optics and data cables. Each individual wire in the strand and each strand in the cable has its own precisely defined twist pitch and tension. This process happens under constant sensor monitoring. Individual tension control prevents internal stresses that could lead to premature metal fatigue failure. Because the layers nest into one another with mathematical precision, the cable becomes less prone to stretching. Using high-strength alloys and precise braiding allows them to reduce the cable's overall diameter without losing breaking strength, which is critically important. To join chains, rods, and rings, a method called flash butt welding is used. The ends of the workpieces are brought together under high-voltage discharges. At the contact zone, a series of metal micro-explosions occurs, literally burning out all irregularities, oxides, and contaminants. This guarantees perfect surface cleanliness before joining. When the metal heats up to a plastic state, the machine executes a sharp impact motion, compressing the parts under enormous pressure. Atoms from both pieces form shared bonds, creating a monolithic structure that's just as strong as the base metal. The weakest point of any weld is the excess molten metal that gets squeezed outward. If left behind, it becomes a source of stress concentration and microcracks. The built-in deburrer does its job instantly while the metal's still scorching hot. Special cutting blades flow around the part's shape, whether it's a ring or a link, shearing away excess metal flush to the surface. Because the removal happens in the hot state, the metal doesn't experience the mechanical shock that comes with cold grinding. The smooth weld lets the chain or ring glide through pulleys and guides without friction or vibration, a must for safe operation over decades to come. This synergy of twisting and precision welding creates structures that stand up to dynamic loads for decades, all while staying lightweight and cost-effective to manufacture. A steel pancake 5 inches thick. That's the blank for a hemi head, the part that holds pressure in chemical plants like a lid on a pot of boiling volcano. At ICM WADA, they toss it into a furnace, heat it to 1832 degrees Fahrenheit. The steel goes soft like Play-Doh. Then a giant press weighing hundreds of tons shoves it into a metal die. Once, the pancake buckles. Twice, deeper still, 3 times, almost a hemisphere. Each pass takes 10, maybe 20 seconds, because it cools fast, so back into the furnace and repeat. Then with a hammer, like in a blacksmith shop, they pound out the curve to make it even. Cool it slowly so it doesn't crack, normalize it in the furnace for strength, and ultrasound scans the inside, like an X-ray, catching bubbles or cracks. The finished head withstands pressure up to 500 atmospheres. Next is flanging. They lay flat steel on the table. The machine grabs the edge and bends it up like a can lid. 90 degrees, thickness up to 2 inches. Hydraulics press evenly. A computer monitors to keep it from bending crooked. For pipe joints, where a seal saves you from an explosion. Then a machine with 800 tons of force stamps in the curves. The part sits on the die. The ram comes down. Metal flows like dough, forming arcs or bowls in minutes. And in New Zealand, a 1,000-ton press brake takes a 20-foot plate. Bam! Bends it in half like a sheet of foil. slowly, with a loud creak, shavings flying. Biggest in the country, cuts metal for ships or bridges without breaking a sweat. And for dessert, the Bronneberg Super 3, a scrap baler, like a compressor for metal. A box with toothed walls, steel, aluminum, cables get dumped in by the pile. A lid with knives drops from above, cuts everything like pruning shears, no pre-cutting needed. Hydraulics press it into a 3-foot cube. Oil heats or cools to prevent overheating. No foundation required, sits right on the ground, remote control operation. Press a button, and out comes a bale, dense as a brick, weighing a ton. Easy to haul for remelting, saves space and gas. These machines are like recycling superheroes, turning trash heaps into fresh steel without the mess. Oxygen lance cutting of a 16-ton cast iron shaft. First, gondola cables. Not your ordinary ropes, but thick monsters the diameter of a beer can, woven from thousands of wires. Each cable is twisted separately, like braiding a giant rope, with built-in cables for internet and lighting in the cabins. They handle speeds of 14 miles per hour, cabins with people at skyscraper height, and last 40 years because they're lighter and cheaper to transport. Nearby, a machine welds chains and rods. You place the metal in clamps, an electric discharge strikes, like lightning, and the ends fuse into a solid seam. Then, a milling cutter removes imperfections in seconds, so there are no sharp edges that could injure or snag anything. Perfect for cranes and lifts, no cracks or warping. Next, a welder for reinforcing pipes. Takes rods, wraps them in a spiral of wire, changes the shape to oval, saves up to half the steel, but same strength. The machine spins, welds, feeds. Out comes a cage for concrete manholes from small to massive, no unnecessary manual work. Toyota crankshafts are cut from a solid metal billet, 5.5 inches in diameter. The machine mills the curves, turns the journals, balances the weights, drills the oil passages, all in one shot, no repositioning. Then furnaces harden it. Cold nitrogen makes it stronger. Grinding brings it to a shine. Perfectly round, zero tolerance. Giant lathe for train wheels. Locks the bogie, strips metal from wheels and brakes. Cast iron base kills vibration. Chips break down automatically, and the cars roll smooth again. No risk of derailment. Robotic machine with twin spindles. The robot grabs a fresh blank while the old one's spinning, turns it, mills the sides, cuts teeth, flips it to the other end, no stopping. Cuts pockets, contours, everything in one cycle, like a speed assembly line. Fatzer AG twists cables over 40 tons, locked coil ropes for bridges, plus spiral types with sockets. They produce complete batches of 420 cast terminals, ready for installation, for suspension structures like pedestrian bridges in Germany. Cage welders, BSM, ISM 250R models, turn out round or oval reinforcement for pipes, up to double layers without a second operator. Programmable spiral pitch, diameters from 13 to 142 inches. They save 50% on steel. For medium volumes, dozens of cages per hour, with touchscreens and LAN. Underfloor wheel lathes for train wheels, machine locomotive and car bogies under heavy loads. The portal passes straight through, reprofiles wheels and brakes, chips the shavings. Throughput, 20 bogies per shift depending on wear. Quick turn robotic machines slash cycle times by roughly 40%. Spindle hits 4,000 RPM. Y-axis travel, 4 inches. Grippers reach about 13 inches. Multitasking means one part in 10 minutes instead of hours. Fatzer AG is a Swiss outfit out of Romanshorn, founded back in 1836 as a hemp rope factory for ships and fishermen. Today, they're leaders in steel cables for mines, bridges, ski lifts. Take the Fury Trockener Stig ropeway in Zermatt. They shipped 2 cables, 70 tons each. Delivery through narrow bridges at night, full cycle from design to installation. They do turnkey cables, tension testing up to 750 tons, embedded fiber optics, splicing. What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, only to be reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore ignite like little controlled earthquakes. In this video, you'll discover things you never suspected, and by the end, the main secret will be revealed that will forever change how you think about zinc. Zinc is the fourth most consumed metal in the world, right after iron, aluminum, and copper. That alone tells you just how critical it is for the global economy and industry. Annual worldwide zinc production runs somewhere between 12 and 13 million metric tons. We're talking massive volumes here, which really drives home how irreplaceable this metal is across hundreds of different applications. The main zinc mining regions are China, Australia, and Peru. These three countries together account for a huge chunk of global zinc ore production, making them the key players in the market. For instance, China isn't just the world's largest producer, it's also the biggest consumer of zinc, which reflects its massive industrial growth. Other major producers include India, the United States, Mexico, and Canada. As for reserves, the US Geological Survey estimates that global zinc reserves sit at around 250 million metric tons. Beyond that, there are what we call resource bases, essentially potential deposits that haven't been fully explored yet, or aren't economically viable to mine right now. These are estimated at over 1,800,000,000 tons. These numbers tell us that zinc, unlike some rare metals, will be around for many decades to come, even with consumption on the rise. The biggest user of zinc is the galvanizing industry, which uses it to protect steel from corrosion. This sector accounts for roughly 60% of all zinc produced. This shows just how critical zinc is for construction, automotive manufacturing, infrastructure production, and countless other industries where steel's strength and durability are essential. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a huge spike in resource demand. 15 to 20% of zinc is used to produce alloys like brass and die casting alloys. These alloys are used in making parts for cars, household appliances, toys, plumbing fixtures, and electronics. Another 10 to 15% goes into making zinc oxide and other chemical compounds. Zinc oxide has a ton of uses, from sunscreens and cosmetics to paints, ceramics, the rubber industry, and even animal feed supplements. Its antibacterial and protective properties make it a versatile ingredient. The rest of the zinc goes into battery production, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, since zinc is essential for the human immune system. When it comes to pricing, like most commodities, zinc prices fluctuate based on global supply and demand, economic cycles, and the situation in major producing and consuming countries. However, demand for zinc remains stable or growing, driven by urbanization, infrastructure development, and the worldwide need to protect metals from corrosion. This makes zinc an important indicator of global economic health. Most zinc is extracted from underground mines. These are entire underground cities stretching hundreds of feet and sometimes several miles beneath the Earth's surface. We're not talking about simple holes in the ground. These are networks of tunnels, shafts, ventilation systems, and hoisting structures. It all starts with exploration. Geologists work like detectives, searching for what's called ore bodies, sections of rock where the concentration of zinc is high enough to make mining it profitable. Now, zinc typically shows up as a sulfide ore, like sphalerite, and it almost always comes bundled with lead, silver, and sometimes copper. Once they've located a deposit, the real work begins: building the mine itself. This involves sinking vertical shafts that serve as the main access points for getting to the ore, hauling materials up and down, and moving equipment in and out. They also create horizontal tunnels, what miners call drifts, that lead straight to the ore veins. The actual ore extraction is where things get dynamic and risky. Miners bring in specialized gear, powerful drilling rigs that bore holes into the rock face, called blast holes. These holes get packed with explosives. Then comes the carefully controlled blast that breaks apart massive volumes of rock. Think of it like a controlled earthquake on a smaller scale. Dramatic, but completely under control. The dusty air is quickly removed by powerful ventilation systems, which also bring fresh air deep underground. The blasted ore is then loaded into massive underground haul trucks or onto conveyor belts using heavy-duty loaders. It's like a non-stop underground highway, constantly moving tons of ore to the main hoisting shafts. From there, the ore is lifted to the surface using powerful elevators or specialized conveyor systems that climb hundreds of feet vertically. At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a processing plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore feed into crushers that break them down into smaller pieces with a deafening roar. This crushed ore then goes into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore gets ground down into an extremely fine powder, almost like flour. This is critical to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder gets mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. Particles of zinc mineral latch onto these bubbles and float up to the surface, creating foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can pack up to 60% zinc. Since zinc often hangs out with lead, the plant might run several flotation cycles to separately pull out zinc concentrate from lead concentrate. The zinc concentrate you get, it's still not pure metal. It's got to go through metallurgical processing to turn into actual metallic zinc. And this is where we enter the world of extreme temperatures. If they're using the pyrometallurgical method, the zinc concentrate first gets roasted. The concentrate is heated in special furnaces at around 1,800 degrees Fahrenheit. This burns off the sulfur that's part of the sulfide ore, converting it into zinc oxide. During this process, the sulfur transforms into sulfur dioxide gas, which gets collected and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable byproduct. Next, the zinc oxide gets mixed with coal and heated to even higher temperatures, over 2,200 degrees Fahrenheit, sometimes reaching as high as 2,700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process takes place. The carbon strips away oxygen from the zinc oxide, releasing pure metallic zinc. And here's where that amazing evaporation effect happens. At these temperatures, the metallic zinc transitions into a gaseous state. Basically, it evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is way higher, zinc literally turns into vapor that rises up and gets captured in special condensers. There, the vapor cools down and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or pellets. Every year, the world mines millions of ounces of a metal most people never even think about. But without it, modern civilization would literally grind to a halt. What if I told you there's a metal hiding in every car that can absorb hydrogen hundreds of times its own volume, operate at temperatures over 5,000 degrees Fahrenheit, and cost more than gold? Palladium seems invisible, but it's what cleans the exhaust from millions of vehicles, drives key chemical reactions, and determines the price of entire industries. Where does it come from? Why is there so little of it? And what hidden detail at the end of this video will change how you think about this metal forever? Stick around to find out. Palladium is a chemical element from the platinum metals group that combines rarity, high chemical stability, and exceptional physical properties. In the periodic table, It has atomic number 46 and a silvery white color that persists even after prolonged exposure to air. At a density of around 7 pounds per cubic inch, it's lighter than platinum, yet strong enough to withstand significant mechanical stress. Palladium's melting point sits at approximately 2,830 degrees Fahrenheit, and it boils at temperatures exceeding 5,400 degrees Fahrenheit, making it suitable for high thermal load applications. One of palladium's most fascinating features is its ability to absorb hydrogen in amounts hundreds of times greater than its own volume. At room temperature, the metal literally pulls hydrogen atoms into its crystal lattice, forming solid solutions. This property is actively used in hydrogen purification technologies, membrane systems, and alternative energy research. Palladium maintains its stability and doesn't crumble, which sets it apart from many other metals. The industrial importance of palladium is enormous. The bulk of global consumption goes into catalytic converters for automotive exhaust systems. In these devices, palladium accelerates the oxidation of carbon monoxide and unburned hydrocarbons, converting them into less harmful compounds. A single passenger car might use only a few hundredths of an ounce of the metal, but with millions of vehicles in play, total demand hits tens of thousands of pounds per year. It's this industry that makes the palladium market incredibly sensitive to shifts in global auto production and environmental regulations. Beyond the automotive world, palladium is everywhere in electronics. It shows up in multi-layer ceramic capacitors, contact assemblies, connectors, and microchips. Thin palladium coatings shield components from corrosion and wear, maintaining stable conductivity even after thousands of power cycles. In electronic components, the metal's mass is usually measured in fractions of an ounce, or even grains, but collectively these amounts carry serious economic weight. Jewelry wouldn't be the same without palladium. It's added to gold alloys to create white gold without using nickel, crucial for people with sensitive skin. Pure palladium is used to make rings, earrings, and watches because it's lighter than platinum and more comfortable to wear. Palladium pieces hold their shape, don't tarnish, and rarely need polishing. Geologically speaking, palladium is pretty rare. Its average concentration in Earth's crust is just a few millionths of a percent. Major deposits are tied to magmatic complexes and sulfide ores, where palladium occurs alongside platinum group metals, nickel and copper. Mining often takes place at great depths, sometimes several thousand feet below the surface, which makes the process significantly more complex and expensive. Because of this, the price of palladium can fluctuate sharply depending on the political stability of mining regions and the state of the global economy. The chemical behavior of palladium makes it valuable in laboratory practice. It's one of the key catalysts in organic synthesis reactions, particularly in carbon-carbon bond formation processes. Thanks to this, palladium plays an important role in the production of pharmaceuticals, agrochemicals, and specialty polymers. Even microscopic amounts of the metal, measured in milligrams or grains, can substantially impact the speed and selectivity of reactions. Palladium's physical properties are equally noteworthy. It responds well to cold working, rolls easily into thin sheets, and draws into wire. From a single ounce ingot, you can produce a sheet covering several square feet. At the same time, the metal maintains high electrical and thermal conductivity, making it useful in specialized technical applications. Palladium is almost never mined by itself. It's a byproduct of nickel, copper, and platinum metal extraction. Everything starts in underground or open pit mines, where sulfide ore is pulled from depths of hundreds or thousands of feet. The ore is crushed and ground into a fine powder, then mixed with water and reagents and subjected to flotation. The result is a concentrate enriched with copper and nickel sulfides and traces of palladium. Next, the concentrate gets roasted in furnaces at temperatures exceeding 1600 degrees Fahrenheit, stripping away sulfur and organic residues. The resulting material is melted, separating into a metallic phase and slag. At this stage, palladium is still mixed with other platinum group metals. Separation begins at refineries, where alloys are dissolved in acids and subjected to multi-stage chemical purification. Platinum, rhodium, and iridium are precipitated sequentially, while palladium is isolated as salts, which are then reduced to metal. The final stage of palladium extraction begins when, after a long chain of chemical purification, the metal has been separated from other platinum elements and exists as salts or spongy precipitate. This material is thoroughly rinsed with distilled water to remove traces of acids and impurities, then dried in furnaces at temperatures of several hundred degrees Fahrenheit. It looks like a gray-black powder with very low bulk density, which doesn't yet have the properties of compact metal. Next, the powder or palladium sponge is fed into melting facilities. Most commonly, induction or electric arc furnaces are used, where the metal is heated in crucibles made from inert materials. The atmosphere inside the furnace is monitored especially carefully. Argon is introduced, or the space is evacuated to prevent oxidation and losses. The temperature is gradually raised above 2,800 degrees Fahrenheit until the palladium particles fuse into a uniform molten mass with a mirror-like surface. When the metal is fully molten, it's held in the furnace for a set period to even out the composition. Even traces of other metals are measured here in fractions of an ounce per ton, so samples can be pulled directly from the melt for lab analysis. If purity doesn't hit the target level, the melt goes back for additional refining. Only after confirming readings above 99.9% is the palladium cleared for forming. To produce ingots, the liquid metal is carefully poured into preheated graphite or steel molds. The weight of these ingots can range from a few ounces to tens of pounds, depending on customer needs. Cooling happens under controlled conditions to avoid internal stress and cracks. After solidification, the ingots are removed, weighed, marked, and the chemical composition is checked one more time. If palladium is destined for catalysts or the chemical industry, it might skip the ingot stage entirely and be turned straight into powder. To do this, the metal is dissolved again, then reduced under controlled conditions to produce particles of a specific size. This powder gets packed into airtight containers, where every single gram carries serious value. Global palladium production is typically measured in the hundreds of thousands of troy ounces per year. On average, worldwide output hovers around 6 to 7 million ounces annually, with more than 2/3 of that volume coming from just 2 countries. Another key figure, secondary recycling, mostly from used automotive catalytic converters, accounts for 25 to 30% of global supply. By comparison, for many other precious metals, the recycling share is significantly lower. In your average ore, the palladium content is incredibly tiny. We're talking a few hundredths of an ounce per short ton of rock, sometimes even less. That means to get just 1 pound of pure metal, you need to process thousands of tons of ore. That's exactly why production costs are so sensitive to energy expenses and logistics. What if I told you that inside the most dangerous machines on the planet hides a steel secret that can only be created once, and a mistake costs an entire nation? That there's an ingot that cools underground for 6 weeks and withstands pressure that would shatter mountains? This giant is born in fire, exceeding 5,000 degrees Fahrenheit, endures months of forging, blows of tens of thousands of tons, and thermal shocks that would explode ordinary metal into fragments. Stick around till the end. You'll discover what these monoliths are actually built for, and why, without them, the modern world would simply grind to a halt. It all starts in the foundry. To create a monolithic ingot, you need liquid steel of impeccable quality, poured into a mold in one continuous stream. This is a stage that demands maximum coordination, because we're talking about thousands of degrees and hundreds of tons of metal. A striking example of such an engineering feat was a record-breaking pour carried out by the British firm Sheffield Forgemasters in 2015. The company's metallurgists successfully handled the pouring of 607 tons of liquid steel into a giant casting pit. To put that volume in perspective, it's nearly the weight of a full-sized Airbus A380 passenger jet. The pouring process is critically important. The steel must not only be melted, but also purified to a level that meets the strictest customer requirements. For example, for reactor components. This means minimizing impurities, gases, and slag. A continuous pour ensures that there won't be any layered defects or boundaries in the ingot structure that would reduce its mechanical strength. During casting, the steel must be fully degassed. Oxygen and nitrogen levels are controlled at levels often not exceeding 20 parts per million. Excess gases can cause microvoids to form inside the monolith during cooling. Immediately after pouring the molten metal, which can exceed 2700 degrees Fahrenheit, time becomes the most critical factor in this process. Unlike small ingots that can cool quickly, a steel giant weighing hundreds of tons cannot be cooled rapidly. If cooling happens too fast, it leads to massive internal stresses, cracks, and structural defects because the outer layer solidifies while the steel inside is still liquid. To ensure uniformity of the crystalline structure, the 607-ton ingot was left to cool in the casting pit for 6 weeks. This is a controlled, incredibly slow process, during which the steel gradually solidifies, dropping to a temperature of around 2000 degrees. This slow crystallization allows the metal to avoid unwanted phase transformations and guarantees a high-quality macrostructure, which is the key to the strength of the future component. Only after this lengthy solidification period is complete, the steel monolith, which after shrinkage and removal of the defective top portion weighs approximately 320 tons, is carefully extracted from the ground. The extracted ingot, despite its weight, is not yet a finished blank. It has a cast, coarse structure with large crystals. To transform it into strong, homogeneous metal capable of withstanding extreme loads, forging is required. Forging 500-ton ingots demands hydraulic presses with working forces ranging from 10,000 to 20,000 tons. For example, forging the largest reactor components requires presses with a capacity of 40,000 tons. Before forging, the ingot is again carefully heated in specialized furnaces. This process can take weeks to guarantee uniform heating throughout the entire volume of metal. The forging itself is done on giant hydraulic presses capable of creating pressure in the tens of thousands of tons. The press breaks down large, brittle cast crystals. The pressure compresses the metal, eliminating microscopic voids that may have formed during casting. The metal gains a directional fibrous structure, which significantly increases its strength, toughness, and fatigue resistance. The forging process for such an ingot takes several months. It's a constant cycle of heating, pressing, rotating, and reheating. Each press stroke is a precise calculation aimed at achieving the required internal geometry and mechanical properties. The energy needed to maintain the furnace for heat treating ingots during a 2-week cycle can exceed 100,000 kilowatt hours. That's comparable to the annual electricity consumption of dozens of typical households. During heat treatment, the allowable temperature deviation in the furnace throughout the entire volume can be only 40 degrees, which requires the use of high-precision multi-zone control systems. After shaping the ingot, we move to heat treatment. This is the final, critically important stage for tuning the internal structure of the steel. A multi-ton steel monolith that's just survived months of casting and forging is like a clumsy giant whose final character hasn't formed yet. It's strong, but its internal structure is still chaotic, riddled with invisible internal stresses. The first step is normalization, or, as we call it, homogenization. The idea is simple. We basically stir the metal structure so it becomes absolutely uniform throughout the entire volume. This ensures that at every point in the workpiece, both on the surface and deep inside, the steel has identical properties. It's like evening out the temperature in an oven so your cake bakes perfectly. Then comes the most dramatic moment, quenching. The workpiece is heated to a very high temperature, bringing it to peak plasticity. And then, rapidly, but under strict control, it's cooled. This could be a water or oil bath. This shock to nature transforms the soft steel structure into something maximally hard and strong. This gives the part its core fighting strength, but there's one side effect. the metal becomes brittle as glass, and massive internal stresses appear. If you leave it in this state, it can crack from the slightest impact. That's why the final, and most humane stage, is tempering. The piece is carefully reheated, but this time to a much lower temperature. The goal isn't to change the strength, but to release the internal stresses that formed during rapid quenching. This process is like taking a deep breath after stress. It increases the steel's toughness, making it resistant to impacts and loads, eliminating brittleness. Only after successfully completing this full month-and-a-half cycle of character hardening is the steel ready to become part of a reactor or a giant press. But what are these steel giants for, into which so much time and resources have been invested? They become critically important components in industries where the price of failure is unacceptably high. For example, in nuclear power, these ingots are transformed into key components of high-pressure reactors. Picture this: pressure, temperature, and radiation demand absolute reliability. And there can't be any seams or welds that might give way. You need just one thing: a solid, continuous monolith capable of withstanding extreme loads for decades. In heavy machinery, these giants become frames for the world's largest presses. These presses shape automotive frames, aircraft parts, and ship components. A frame that won't deform under thousands of tons of load has to be cast in one piece. And of course, there's power generation, rotors for the largest steam turbines, or crankshafts for massive marine engines that drive supertankers and container ships. In these components, you need guaranteed strength against bending and secondary loads, and only steel produced through this incredibly complex process can deliver that. What if I told you the world's toughest roads and roofs aren't born on construction sites, but inside the blazing hot heart of crude oil? A material that withstands temperatures of 360 degrees Fahrenheit and bitter cold, yet turns to stone with just one technologist's mistake. But why did this black, sticky residue at the bottom of an oil column become the foundation for bridges, airstrips, and massive warehouses? And what chemical secret lets it survive for decades without cracking under the weight of 40-ton trucks? Stick around till the end. You'll discover what even some manufacturers keep hidden. Tar can be wood-based or petroleum-based, but for construction and roofing, they usually mean petroleum tar, which comes from processing crude oil. After fractional distillation, when gasoline, diesel, and light components have been separated out, a heavy tail remains at the bottom of the column, a thick residue. It's then heated in large furnaces and distilled under vacuum to evaporate even more fractions that'll be used for lubricants and paraffins. What's left after squeezing out these heaviest parts becomes the base for bitumen and tars. Then the chemistry kicks in. Other components are added to reactors. For example, lighter oils, polymers, modifiers, sometimes sulfur. And at temperatures around 900 to 1200 degrees Fahrenheit, the mixture is held so that large organic molecules partially cross-link, becoming more viscous and heat-resistant. The result is a thick, extremely sticky material that becomes hard or glass-like when cooled. It can be crushed into chunks, dissolved in organic solvents, or heated to a liquid state and applied as a waterproofing layer. Bitumen is a close relative of tar, but with a clear focus on road construction and roofing. It's also obtained from heavy petroleum residues after vacuum distillation. In large-scale bitumen production, it's not so much about pure chemistry as it is about fine-tuning viscosity and temperature behavior. If bitumen is too hard, it'll crack in winter. If it's too soft, it'll flow in the heat when asphalt hits 100 degrees. That's why the industry has a concept called penetration, how deep a needle sinks into a sample at a specific temperature and load. Engineers tweak the ratio of light and heavy fractions, add polymeric modifiers to create a material that won't flow in scorching heat and won't turn brittle in freezing cold. In massive mixers, bitumen gets heated to temps ranging from 480 to 660 degrees Fahrenheit, and with intense stirring, they introduce modifiers, mineral powder, sometimes acidic or alkaline additives to stabilize the structure. That's how polymer-modified bitumens are born, for high-performance roads, airport runways, bridge expansion joints. When people say asphalt road, they're actually talking about a mix of mineral materials, meaning gravel, sand, mineral powder, with bitumen as the binder. Inside enormous asphalt mixers, gravel gets pre-dried and heated to temps close to 300 degrees Fahrenheit to eliminate any moisture. Then they add hot bitumen and mix until every single stone is coated with a thin film of binder. The hot mass gets loaded into dump trucks, then heads off for laying. If the bitumen's made wrong, you'll see ruts, cracks, and potholes within a few seasons. If the technology's dialed in, the surface will hold up for years under trucks weighing dozens of tons. Roofing felt, it's the story of turning a simple roll of base material into a durable shield against rain, UV rays, and temperature swings. The foundation is cardboard, fiberglass, or polyester mesh in roll form, about 3 feet wide. Cardboard base gets chosen for budget materials and light-duty applications. Fiberglass, when you need better heat resistance and less warping, and polyester, for steeper roofs where flexibility and tear resistance matter. All these bases share one trait: they're porous, so without impregnation, they soak up water easily and break down fast. To transform a bare base into a waterproofing material, the roll passes through a production line with baths of hot bitumen or bitumen tar compounds. Liquid bitumen is heated to a range of 450 to 570 degrees Fahrenheit, sometimes higher, to reduce viscosity and ensure quality penetration into the fibers. The roll is fed on rollers into the bath so that it's completely submerged in the melt and passes through at a controlled speed. During this time, the bitumen fills the pores of the cardboard or fabric, displaces air and moisture, forming something like a skeleton flooded with waterproof mass. After exiting the bath, excess material is removed by calibration rollers. This helps maintain the specified thickness and avoid drips. Next comes the coating stage. The saturated base passes under bitumen or tar applicators that lay down the main layer on both the bottom and top. They use knife or roller coaters for this. A thin gap between the roller and backing plate meters out the coating thickness, typically within a few tenths of an inch. The bottom layer handles bonding to the roof deck or substrate, so they might add more elastic plasticizers, polymers, oils, special additives that cut the risk of cracking during bending and temperature swings. The top layer works as armor against sun, rain, hail, and mechanical damage, so they make it harder and more heat resistant, sometimes modifying it with polymer for better UV resistance. While the top layer is still hot and sticky, it gets coated with mineral granules. A hopper sits on the line, steadily pouring mica chips, basalt aggregate, or slate onto the moving belt. The particles instantly embed themselves into the soft bitumen and lock in place as it cools. This coating isn't just for a nice rough texture. It acts as a shield against ultraviolet radiation. The sun heats the exposed bitumen surface less, the material ages slower, and it doesn't crack as fast. Plus, the granules boost abrasion resistance. You can carefully walk on this roofing during installation and maintenance without smearing or tearing off the top layer. After the granules are applied, the belt passes through a cooling zone. Here they use either air cooling or systems with water baths and chilled rollers that pull heat away from the hot bitumen. It's crucial for the temperature to drop to a safe level before winding into rolls. If you roll up hot material, the layers will stick together, the geometry gets thrown off, and the granules can lose their grip. To monitor parameters on the line, they install temperature sensors and thickness gauges that watch to make sure the coating layer doesn't come out too thin or too thick. A thin layer means future leaks. Too thick means wasted bitumen and problems during rolling and installation. The next stage is cutting and winding. The roofing felt strip gets cut lengthwise or crosswise into standard rolls, most often 30 to 50 feet long. Each roll is tightly wound onto a core, so the edges don't shift and the top layers don't slip. Sometimes on one side, they leave a strip without granules, covered with clean bitumen. During installation, this strip gets overlapped by the adjacent sheet, forming a watertight seam that film or granules won't prevent from heating with a torch. Polyethylene or paper interlayers are added to the roll so the layers don't stick together during shipping and storage. The finished material gets labeled. The tag shows the base type, pounds of bitumen per square foot, granule type, flexibility temperature, and other specs that matter to designers and installers. But the story doesn't end there, because how roofing felt behaves on a roof heavily depends on what exactly they mixed in back at the factory. If you use plain oxidized bitumen, the material will be cheap but sensitive to temperature swings. On a sunny roof, where in summer the surface easily heats up to 180 degrees, that layer gradually loses elasticity, becomes hard and brittle. To prevent this, polymers are added to the binder. The first makes the material more elastic in the cold. The second holds up better at high temperatures. That way, roll roofing can easily survive both winter freezes and summer overheating without developing a web of cracks. It's polymer modifiers that gave roll roofing new life in the competition with membrane roofing systems. Picture a warehouse complex roof spanning several tens of thousands of square feet. The classic setup: leveled base, a layer of bitumen emulsion primer, then multiple layers of roll material with a 3 or 4 inch overlap. The bottom layer is often torch applied. You flip it granule side up, heat it with a gas torch until the bitumen softens, and roll it onto the base. The top layer goes down the same way, forming a continuous membrane where the seams are the most critical zones. It's the seam quality that determines whether the roof leaks or not. If the factory left the right strip without granules, installers can more easily ensure good fusion between the layers. Choosing the base is just as important. Cardboard works fine on small buildings and temporary roofs, but it's afraid of prolonged moisture and deformation. Fiberglass barely stretches, so the roofing holds its shape, but if the base flexes too much, cracking is possible. Polyester base behaves like a dense elastic mesh. It can give a little along with the substrate without tearing the bitumen layer. For roofs where microsettlement, structural movement, or small vibrations are possible, polyester provides extra strength reserve. That's why modern standards for flat roofs increasingly feature polyester-based materials with polymer-modified bitumen. Another interesting detail: the color of the granules. The traditional option is dark gray or black basalt, which hides dirt well but heats up aggressively. For energy-efficient buildings, manufacturers produce rolls with light-colored, sometimes nearly white granules. This type of roof reflects most of the solar radiation, and the surface temperature on a hot day can be dozens of degrees lower. That cuts the load on air conditioning and makes the climate on upper floors more comfortable without any extra energy costs. In commercial centers and warehouses, that's noticeable savings over years of operation. Behind this entire production chain lies another important aspect: environmental impact and worker safety. Roofing felt gets made at high temperatures, which releases bitumen fumes and organic compounds into the air. Modern production lines install exhaust and filtration systems, so workers aren't basically inhaling smoke all day. To cut emissions, some factories are switching to water-based primers and emulsion blends instead of straight solvents. And when you're tearing off old roofs, disposal becomes an issue. Crews strip the old membrane in big chunks, shred it up, then either burn it in specialized furnaces with filters or partially recycle it into road mixes as an asphalt additive. Every year, billions of people around the world touch chromium on faucets, cars, appliances, and almost no one realizes that behind this cold shine lies one of the most dangerous chemicals in modern industry. How can a metal that makes steel stainless and withstands jet engine temperatures simultaneously poison water, air, and the workers who handle it? In this video, we'll step behind the doors of mines, furnaces, and electroplating tanks. Witness how gleaming surfaces are born from toxic dust and molten metal, and by the end, reveal a property of chromium that even many engineers don't suspect. Watch through to the finale, and you'll never look at an ordinary chrome-plated faucet in your own bathroom the same way again. Chromium is a metal that simultaneously attracts with its shine and intimidates with its dangers. In pure form, it displays a cool silvery blue color, exceptional hardness, and polishes beautifully to an almost mirror-like surface. It's precisely this thin layer of metallic chromium on parts that gives us the familiar chrome look, from pickup truck bumpers to bathroom faucets. A coating just a few thousandths of an inch thick can transform ordinary steel into a brilliant, visually premium material that also resists corrosion better. But beneath this gloss hides a complex technological chain and toxic chemistry, especially during the mining and ore processing stages. The primary source of chromium is the mineral chromite. It's extracted in quarries and mines, where the rock is drilled, blasted, crushed, and sorted. Dust from the ore contains chromium compounds in various oxidation states, and some of them are toxic to the lungs and skin. So mines and processing plants require serious dust and gas cleaning systems, along with personal protective equipment. After crushing, chromite undergoes enrichment, flotation and gravity separation, to separate the valuable mineral from waste rock. Concentrate with chromium content above 45% is sent to blast furnaces or electric furnaces, where at temperatures exceeding 3,600 degrees Fahrenheit, it's reduced with carbon to produce ferrochrome, an alloy of iron and chromium. It's ferrochrome, not pure chromium, that serves as the main workhorse for metallurgy. The majority of all extracted chromium goes into producing stainless steels. If you add 10 to 26% by mass of chromium to molten carbon steel, an extremely thin but highly resistant oxide film forms on the surface. It self-heals when damaged and protects metal from rust even in humid or aggressive environments. That's how we get kitchen sinks, railings, medical instruments, and chemical reactor tanks that maintain their appearance for years. Imagine a chemical storage tank holding several thousand gallons. Adding chromium to the steel allows it to withstand contact with solutions that would have corroded ordinary structural steel long ago. Another crucial area is heat-resistant alloys. Chromium increases heat resistance and wear resistance, which is why it's incorporated into steels for turbine components, nozzles, and internal combustion engine valves operating at temperatures exceeding 1500 degrees. Combined with nickel and cobalt, these form so-called superalloys used in jet engines and power plants. Where steel must withstand both high temperatures and powerful mechanical loads, chromium is nearly indispensable. Even ball bearings in high-speed machine tools contain chromium steel, so the raceways don't break down from impact and friction. Chromite is also used without converting it to metal. It's made into refractory materials for furnace linings, where temperatures reach 3,000 degrees. A mix of chromite and magnesite aggregates withstands sudden temperature changes and contact with slag without breaking down. These linings cover the walls of cement rotary kilns, converters, and smelting units in ferrous and non-ferrous metallurgy. Chromite sands are used as molding mixtures in foundry work. They don't react with molten steel, have minimal thermal expansion, and allow casting of complex parts with high precision. One of chromium's most recognizable facets is the shine of electroplated coatings. The chromium plating process is electrolysis, where a part made of steel or another metal is immersed in a chromium salt solution and current is passed through the bath. A thin layer of metallic chromium settles on the surface, ranging from a few micro-inches in decorative coatings to several thousandths of an inch in industrial chrome plating. The thin layer provides aesthetic shine and basic corrosion protection. For example, on automotive trim, tool handles, and plumbing fixtures. Thicker layers are used to enhance wear resistance. Hydraulic cylinder surfaces, piston rods, press molds, and printing press rollers. These components work in contact with abrasive materials and fluids under high pressure, but thanks to the hard chromium layer, they maintain their dimensions and geometry much longer. However, it's precisely during the chrome plating stage and the production of chromium salts that the element's toxicity becomes most acute. Hexavalent chromium, present in certain electrolytes and reagents, is a carcinogen and can cause damage to the skin, mucous membranes, and respiratory tract. That's why modern facilities are implementing closed-loop purification systems, automated plating baths, and localized ventilation, while some industries are gradually switching to trivalent chromium or completely different types of coatings. Many countries enforce strict limits on chromium compound concentrations in workplace air and wastewater, and sludge containers are stored in specialized landfills to prevent toxic ions from leaching into groundwater. Equally fascinating is chromium's role in the color surrounding us. This element's compounds produce vibrant greens, yellows, reds, and oranges. Chromium oxide serves as one of the most stable green pigments for ceramics, road markings, and paints that must withstand sunlight and weathering. Chromates and dichromates once provided brilliant yellow and orange pigments, widely used in artist paints and printing. But due to hexavalent chromium's toxicity, their use is now strictly regulated or replaced with safer alternatives. Nevertheless, in some highly specialized materials, such as ceramic pigments for tile, chromium compounds are still used to achieve the desired shade and color stability during firing. The chemical industry relies on chromium, both as a catalyst and as an active reagent. From sodium dichromate and other salts, a wide spectrum of chromium compounds is produced, which are applied in the manufacturing of textile dyes, mordants for fixing dyes onto fibers, and agents for leather tanning. Traditional chromium tanning makes leather resistant to water, rot, and abrasion, but carries the risk of forming toxic chromium species, so modern manufacturers are transitioning to controlled processes with minimal emissions or alternative systems. Chromates were once included in anti-corrosion primers for aluminum aircraft and ship parts. They suppress the development of corrosion sites, but due to their toxicity, they too are gradually being replaced by less hazardous technologies. Interestingly, in microdoses, trivalent chromium is considered a trace element that may participate in regulating carbohydrate metabolism in the human body. But even here, the working concentration is measured in micrograms per day, and exceeding permissible levels, especially when in contact with compounds, takes on a toxicological rather than biological character. That's why chromium is one of those elements where the fine line between benefit and harm literally runs through an order of magnitude in concentration. If you look at the industrial map of the world, chromite mining centers are located in South Africa, Kazakhstan, Turkey, India, and several other countries. Ore from there travels to metallurgical plants, chemical factories, and electroplating shops, being transformed into stainless steel, heat-resistant alloys, refractories, pigments, and coatings. Products fly across the globe, from kitchens in American suburbs to oil rigs in the Gulf of Mexico, and jet airliners crossing continents at 30,000 feet. The gleam of chrome surfaces in your bathroom, or on a car hood, represents just the visible tip of the iceberg, beneath which lie mines, furnaces, electrolysis baths, and strict environmental regulations. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead built aqueducts, adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now? And where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid.